So, let's dive into one of the deepest, most beautiful questions in all of mathematics. It's a million-dollar mystery, and it's all about a hidden connection between two completely different mathematical universes. This is the story of the Birch and Swinnerton-Dyer conjecture.
To really get our heads around this, let's start with a super simple analogy. Picture a guitar. If I asked you how many strings it has, what would you do? Well, you could just look at it, right? Count them. 1, 2, 3. Easy. Or you could do something totally different. You could close your eyes and just listen to it being played. By figuring out how many fundamental notes it can make, you could arrive at the very same number. So that's two completely different methods, seeing versus hearing, but they both point to the exact same truth. Just hang on to that idea.
Okay, now, let's make things a little more interesting. What if we swap out that simple guitar for something way more abstract? Say, a mathematical equation. And not just any equation, but one that has an infinite number of solutions. How in the world would you count its strings then? How could you possibly grasp its fundamental nature? Well, that is the heart of the problem we're about to unpack.
So first, let's try the direct approach, the equivalent of just looking at the guitar and counting what you see. This path takes us into what mathematicians call the world of arithmetic. It's a world of whole numbers, counting, and tangible points on a graph. You see, the whole conjecture is built on this incredible duality. On one side, you've got arithmetic. That's where we try to literally count the fundamental solutions or points on a curve. Think of it as counting the strings you can physically see. But on the other side, we have a totally different world, analysis. Here, we don't count directly. Instead, we study a special kind of musical function that's tied to the curve. This is like listening to the guitar's music to figure out its secrets.
So, what is this mathematical guitar we keep talking about? It's something called an elliptic curve. It's just an equation that looks something like the one you see here. Now, what's so amazing about these curves is that their solutions, the points that fit the equation perfectly, aren't just a random scattershot. No, they have this deep, beautiful, hidden structure to them.
And that hidden structure brings us to the key number we're trying to find. It's called the rank. The rank is basically the number of fundamental strings on our curve. It's the minimum number of independent points you need to start with to be able to generate all of the other infinite solutions. Finding this one number, that's the main goal when we're in the world of arithmetic.
Okay, so we've had a go at counting the strings directly. Now it's time to, put on our headphones and try to listen to the music. Let's jump over to the other side of this puzzle, the world of analysis.
The song that every elliptic curve sings is called its L function. It's a bit complicated, but think of it like this. Instead of looking at the solutions directly, this function cleverly encodes information about them in a completely different language, the language of prime numbers. It basically weaves together all of this data from every prime number system into a single, unique musical signature for that curve. Now here is the absolutely wild part. Out of this entire, infinitely complex song, this whole L function, the entire mystery boils down to its behavior at one single point. We only need to listen to what the function is doing when its input, which we call S, is exactly equal to 1. That's it. Everything hangs on what happens in that one tiny moment in the music.
Okay, so we have our two worlds, right? We have the number of strings, the rank, which we got from the world of arithmetic, and we have the music, the L function, from the world of analysis. Now it's time for the main event. Let's see where these two worlds collide. So we've been looking at the exact same thing, this elliptic curve, but through two totally different lenses. One is like counting by sight. The other is like understanding by sound, arithmetic and analysis. You could say they're two completely different languages. So the huge question that the mathematicians Birch and Swinnerton-Dyer asked was, are they telling us the same story? And this is the absolutely breathtaking answer they propose. The conjecture says that the rank, that number of strings we counted, is exactly equal to how flat the L function is right at that special point, s equals 1. In other words, it's a measure of how strongly the function hits 0 at that critical spot. The music knows exactly how many strings there are. It's just incredible.
And look, this isn't just some wild guess. We have some really powerful evidence. Check out these examples. For these top two curves, mathematicians were able to calculate that the rank is 0. And guess what? Their L function at s equals 1 is not 0. But then look at the bottom two curves. Their rank is 1. And what happens to their music at s equals 1? Boom, it's exactly 0. The pattern just holds up time and time again for every single case we've been able to check. You can actually visualize this connection, and it's beautiful. If a curve has a rank of 0, its L function's graph doesn't even touch the 0 line at s equals 1. If the rank is 1, it slices right through it. For a rank of 2, it comes down, just kisses the line perfectly flat, and then bounces back up. It's like the flatter the function is at that point, the more contact it makes with 0, the higher the rank is. It's a perfect geometric picture of a deep arithmetic truth.
So this is obviously an amazing, mind-bending connection. But why is it $1 million problem? Why do mathematicians care so much about it? To see that, we need to zoom out a little bit and look at the bigger picture.
Well, this conjecture isn't just some isolated island. It's part of a vast, interconnected web of ideas. It's built upon the famous modularity theorem, the very same idea that was used to prove Fermat's last theorem. It even has these strange, fascinating echoes in theoretical physics, where the rank seems to correspond to the number of zero-energy states in a system. It's because of this incredible depth and its connections to everything else that it's been named one of the 7 Millennium Prize problems, with a cool $1 million prize waiting for whoever can prove it.
When you boil it all down, it all comes back to this one incredibly profound idea. You have analysis, the world of waves, continuity, and music, and you have algebra, the world of counting, whole numbers, and strings. They seem like they couldn't be more different, but they're not. They're just 2 different languages describing the exact same underlying truth. Proving this conjecture would be like discovering a Rosetta Stone for mathematics. And it really leaves you with this final, tantalizing question, doesn't it? What other deep, fundamental truths about our universe are out there, just hidden in plain sight, simply waiting for someone to come along and figure out how to translate between their languages?